Right, so let's quickly discuss the concept of capillary action. And this essentially is the idea whereby a compound moves up a different substance. For example, if you put a piece of paper in, or a piece of filter paper in water, then you'll see it starts to absorb the water. The water kind of moves against gravity, or not kind of, it moves against gravity upwards the filter paper, and you notice how it then what is this phenomenon? And that is exactly what we want to discuss here. And on that same point, it is this idea where you have, in a buret, you have a concave meniscus surface for water, whereas you have a convex meniscus surface for mercury. And the phenomena occurs for two different reasons, which we'll discuss. So, like I say here, it's because of something called adhesion in the case of water. So basically, I mean, like it says, water wants to adhere, or there's an adhesive force for the water to want to climb up against the walls of the buret, right over there, whereas cohesion dominates in the mercury case. So meaning that there's a bigger cohesive force between the mercury molecules than what there is between the mercury and the walls of the buret. So it forms this convex meniscus. All right, so, and in principle or in practice, what you'll actually see is, so here you see it. So here you see the convex meniscus of the mercury, and you see the concave meniscus of the water. So in actual practice. And like I said, the example of the capillary action of the piece of paper that is partly immersed in the water, then the polar molecules are attracted to the cellulose of the paper, and then the water moves up in the paper. And so you can see that even though it's just touching over there. So I mean, it's these kind of interactions. So it's essentially, it's the climbing of water upwards, and it's because there is attraction between water and the SO2 in the silica glass. So it means there is some H2SiO interactions, and these are maximized, meaning that your H2O SO2 interactions want to occur. So they maximize them, and they don't really care about the water-water interactions. They really want to occur between SiO2 and H2O, and they cause this spreading out, this climbing of the water. Whereby in mercury, what is prioritized is the mercury-mercury interaction. So mercury-mercury interactions are maximized, and then the interactions between mercury and glass are minimized, or mercury and the silica oxide is minimized, and that's why you get the convex meniscus. So it sort of pulls it inwards, or it pulls itself upwards, if you want to think about it as such. And that's what we call adhesion. So adhesion is the pulling outwards, and cohesion is the pulling of inwards. So adhesion, meaning we go outwards, we climb up, and cohesion, meaning we form downwards, we group together. So that means ethylene glycol will have a concave meniscus. And the main reason for ethylene glycol, if you look at it, it's not like water. There's no open OH or oxygen silicon interactions that is possible. You could argue, but it's more likely to have a cohesion interaction than what water is possible to have. Water has a lot more hydrogen bonding interactions or other types of other hydrogen bonding interactions than what ethylene glycol is possible to have. But anyway, so there's basically the idea of this example is more for capillary action, to discuss why are these things like that. And of course, some are flat. Some have no meniscus. So that's essentially why. Okay. Thank you for watching. It's a short video. It's just sort of an interesting fact more than it is an example, really. But I hope that is something that you might, when you see it in the lab, you will then understand it and recognize it and know what it is. All right, thank you for watching.